Happy New Year, everybody. We are very happy to have Antoine Browaeys with us today from the Laboratoire Charles Fabry, Institut d'Optique from France. This is, I Googled a bit around to find his CV, and apparently that's also where he did his PhD. So he is a veteran of this institution with 2 years spent at NIST in the laser cooling group. In the meantime, he also supervised or was the external examiner of James Millen's thesis, who is, at least in Zoom, still next to him on my screen. So Antoine, we are very happy to have you here. Please take it away.
Thank you very much, Arne. So thank you. So good afternoon to everyone, and Happy New Year to everyone. Hopefully we'll have a chance to meet again in person sometimes during this year. And so thanks a lot for the invitation. It's very nice to have this chance to talk to you. I mean, there are many people I know, obviously, in Mainz. So what I'm going to discuss today is some kind of overview work of recent subject we've looked at in our group around using arrays of atoms in order to implement many body physics problems. So I mean, for those of you who don't know us, so we're indeed at the Institut d'Optique, which despite this Eiffel Tower here is not strictly speaking in Paris, but actually on the campus of Université Paris-Saclay, which is 20 kilometers south of Paris, which is one of the big science cluster in France. All right, so before I dive too much into the topic, just let me introduce you to the team. So this is our group at the Institut d'Optique. It was a pre-COVID picture, so before the lockdown. Now some people have left, we have new people. But so I will not introduce everyone, but essentially Igor and Thierry are the two permanent staff members in the group from CNRS as well, and each of them are supervising one of the projects we have. And I will try to cover actually the two main projects in our group. So we have a very talented PhD student and postdocs. And for what I'm going to discuss today concerning the many body physics aspect, we also have theory collaborations. And that's kind of essential for us because we are really people coming from the AMO physics world, and therefore background in condensed matter physics is pretty low, so we do need to have inputs from the theorists. And so we have very fruitful collaboration with Andreas Leuchli, who is in Innsbruck, and Hans-Peter Büchler, who is in Stuttgart. So I will show you results, in particular done with Andreas, for what I'm going to cover today. If there are people who are interested as well, we are really and starting to be a bit desperately looking for postdocs. I mean, the period is not necessarily obvious for people to travel and visit, but I mean, if some of you or your students or you know some people who would be interested in experimental physics in our group, please do advertise the fact that we have an open postdoc position. All right, so I will just start by a very general introduction. I mean, I'm pretty sure that many of you know all this, but so the general framework of what we do in our group, and that's the case of really a large number of groups around the world, is to study many body physics using synthetic matter. So the goal of many body physics, roughly speaking, is to study and to understand the behavior of ensembles of interacting quantum particles usually. And I've put here a few pictures of iconic effects in many body physics, you know, about superfluidity, superconductivity, magnetism, quantum magnetism. So these are examples from the solid state physics world, so to speak, or condensed matter physics world. Of course, you do also have many body physics in high energy physics, in cosmology, so neutron star are one examples of this. And of course, we know a lot about this. I mean, there is 100 years of research and in trying to understand them from a quantum point of view, but obviously there are also a lot of open questions still, and especially when the interactions dominates in the problem. And so in many questions, in many cases, for example, people don't even know what is the ground state phase. So the phase diagram as a function of parameters, external parameters. We also have a very hard time to calculate the dynamics, the exact dynamics of the systems when the interactions dominate. I mean, considering the fact that, and the reason for these difficulties, of course, is the exponential scaling of the Hilbert space. Something which is also, I mean, it's not new, but it's a subject which has been developed over the last 30 years is the role of topology in condensed matter physics, and where can you engineer topological bond structure? And also a question that has only been recently asked in the context of condensed matter physics and many-body physics is what is the role of entanglement? So that's where actually it's nice to have this convergence of quantum information theory, solid-state physics, AMO physics, because this kind of question traditionally did not belong to condensed matter physics, but now is seen as a nice way to characterize many-body systems. So, of course, the idea is that as it is very difficult sometimes to answer this question by just performing experiment on real system, we can use the experimental control that we have gained over the years to over AMO physics system, but not only, obviously, to implement directly the many-body Hamiltonians of interest. And I want to emphasize the fact that this many-body Hamiltonian may be either an idealization of one of the situations I've put here, which you cannot calculate exactly, but it can also be purely abstract mathematical Hamiltonians. Like you've got a mathematical physicist who comes up with some kind of Hamiltonians dedicated to the study of some particular symmetries and so on. Now, I mean, there is a large chance that actually you can implement it in the lab. So one nice appealing feature of this is the ability to tune the parameters of the system, and in principle, much more than what you can do with real life system. You can tune the interactions, for example. So that's something which is reasonably new to this system. Okay, so just to make things a bit more concrete, what kind of many-body physics problem are we looking at? Well, usually the first time of many-body physics problem you look or you are introduced to are spin models. So just take an ensemble of spin 1/2 particles. We're going to make it even simpler by pinning the particles in space. And people have written some Hamiltonians to describe that. So I mean, I write two of them here, which I will use in the remaining of the talks. The first one is called the Ising model, the Ising Hamiltonian. And it's essentially saying that if two spins have the same orientation, so either up or down, the energy is different from if they have opposite direction. Okay, so this is written here in this sigma z form. So sigma z is the Pauli matrix, obviously. The second type of Hamiltonian that you encounter is what is called the XY model. The XY model is a flip-flop Hamiltonian which drives the exchange of the state between two spins. So we encounter them in many different contexts. So traditionally, it's magnetism. So can you understand from the properties of the electronic spin, the macroscopic properties of a system, but also in some other areas where you do not even need to have spins which are involved. So for example, photosynthesis is a process which you can describe by this exchange Hamiltonian. And so this is essentially a place where you've got the photons coming from the sun, which arrive on a light harvesting device. It drops energy somewhere, and this energy is carried along this chloroplast until a place where the chemical reaction takes place. And you can describe the transport of this excitation in the spirit of this XY model. Light scattering is another example from an ensemble of molecules, and I will talk about that later. You can also look at the transport of excitons through polymers, also using this Hamiltonian. So it goes well beyond the realm of just spin physics. It's a kind of a generic system to look at many-body physics. So people have looked at different systems, different platforms, and in Mainz, obviously, you've got the ion platforms of Ferdinand, but people are also looking at artificial atoms like quantum circuits, AMO physics system, also like atoms in lattices, magnetic atoms. And photons are also other examples. And so the platforms that I'm going to discuss, I will actually look at two different topics, so to speak. The first one is arrays of individual atoms that are trapped in optical tweezers and that are made to interact by van der Waals interaction, by placing the atoms to Rydberg state. So they are typically, so this is an image of an array containing about 100 atoms. So each of the site, the bright dot here corresponds to, a dark dot, sorry, corresponds to one atom. It's a fluorescence image separated by typically 10 micrometer. And the second system I will look at is, again, an array of atoms, but then the atoms are much closer to each other. Typically, they are separated by an optical wavelength distance. And the interest in those two systems is that they implement different instances of the model that I just discussed, the spin model. So the first one implements the Ising model, if you look at the van der Waals interaction, and the second will implement the XY model. And I will try to give you some ideas of what we've done with this system. Okay. So so this is what I'm going to cover. So I will try first, the first part of the talk, to discuss about the quantum magnetism using the van der Waals interaction. We just show you some last results on this. And the second, I will describe the collective light scattering by an ensemble of atoms. And I try to discuss atomic chains and subradiance in these things. I will maybe, so that it's not too boring to you and there is not only me talking, make a natural break after the first part so that you can ask questions. And of course, please ask questions at any time during the talk, and it makes the things more lively. Okay, so let me start with the quantum magnetism. So this is work that we've been doing with Andreas Löschli last year, essentially, together with his student, Michael Schuler, Thomas Lang, and Alex Eberharter, and they are all in Innsbruck. Okay, so the platform that we use for these experiments is something that was pioneered by Philippe Grangier, actually, in around 2001. The idea is to take a laser beam, to focus it very tightly, and at the focal point to place one and only one laser-cooled atoms. So I don't give you too many details about how we do that, but essentially, this is a way you can have one atom trapped in a tweezer. These atoms, you can see it because you can send resonant light on the atom and you can measure the fluorescence coming from the atom on a CCD camera. So typically the size of the trap is micrometer, therefore it's very small and the atoms are pretty well localized in this trap. The second thing that we need is arrays of such tweezers if you want to do many-body physics. And so that's the thing that we've developed over the years at the Institut d'Optique. The idea is to place in the laser beam that is going to create the dipole trap, we place a spatial light modulator, which is a liquid crystal device that imprints a phase. And when you do so, you are able to have the Fourier transform of this phase pattern, which can have any geometries you wish. So you've got arrays of dots where you can place atoms. So once again, there are lots of interesting experimental detail, but the bottom line is that if you do that, you are able to produce a large array of atoms. So what I show you here are just our latest results from the end of last year. So that's the largest array we can create. Those arrays are fully filled. So they contain up to 200 atoms. So you just take a single shot fluorescence image and you locate where the atoms are. So you have this kind of 209 atoms. So it's a 1D chain, if you wish, which is wrapped on it. You've got these 14 by 14 arrays, these 100 or almost 200 atoms in triangular lattices. Important to us, and it may not be so spectacular to you, but we can also generate any arbitrary pattern. So for example, this is also a fluorescence image of a pattern that you may have recognized. It's just a pixelized version of the Mona Lisa. So it's totally useless for physics, but it was important for us to see that indeed we could prepare any arbitrary geometries and not only Bravais-like geometries. And finally, what we can do is to trap the atoms in 3 dimensions. In a sense, you can do 3D patterns. So this is this Eiffel Tower, but also this kind of Fullerene-like picture. Just have to be careful. Those pictures here are not single shot pictures. They are average so that you have the feeling that all the traps are filled at the same time. Okay. All right, so that's the starting point. We have these arrays of atoms, and essentially the atoms in these arrays, they are pretty far from each other. Distance is a few micrometers, up to 10 micrometers or even larger, and therefore the atoms do not interact. So if you want the atoms to interact at such a large distance, you need to enhance their natural interaction, and the way we do it is by promoting them to Rydberg states. So Rydberg states are nothing but highly excited states that are pretty close to the ionization threshold. So it has 2 consequences. I mean, they are very large principal quantum numbers. They look very much like, this planar system, this solar system where the electrons spiral very far from the nucleus. But this leads to, first, a fairly long lifetime, so typically more than 100 microseconds, which may still look short to you, but it's actually long if you compare that to the few nanoseconds on low-lying transitions. And second, they have very large dipole moment between the 2 neighboring sites, which scale actually as the principal quantum number square. The consequence of this is that the atoms will feature very large dipole-dipole interactions. And so just to give you a number, if you just take two Rydberg atoms separated by about 10 micrometers, for the usual principal quantum number we use, so typically 50, 60, or 200, the strength of the interaction is in the megahertz range. And so this has a consequence, which is that the time scale for any physics driven by the interaction takes place over less than a microsecond. And therefore, you see why this finite lifetime of the Rydberg state can be essentially eliminated, drops out of the problem, because it can be much larger, much longer than the time scale of the interaction. Okay, so in this way, we can explore coherent many-body physics in this system. So if we just stick to the van der Waals interaction, which is the one that occurs if you just look at two Rydberg atoms placed in the very same Rydberg state. So essentially, I would just consider these two atom energy spectrum, where I place the first atom in one Rydberg state, NS, the second one in NS as well. The interaction between them will lead to a diagonal shift. So essentially, this is the shift of this doubly excited state by an amount which scales like C6 over R6. And the thing that makes Rydberg so special is the fact that the C6 coefficient scales like the 11th power of the principal quantum number. So this is a very violent law, which makes the interaction switchable. If they are in the ground state, they do not interact. If you promote them to the Rydberg state, they will have an energy which is enhanced by 100 billion, essentially. So that's a lot. So now if you want to describe that by an Hamiltonian, what you do, you just write an Hamiltonian which has this diagonal form. So it's a C6 over R6 times N1, N2, where N1 and R2 are the Rydberg occupation number. So unless the two are equal to 1, which is to say the two atoms are in the Rydberg state, the interaction is 0. Okay, and so with this, we're going to be able to implement this Ising model using this van der Waals interaction. And the way we do it, we need also something that couples the ground state to the Rydberg state. So essentially, this is the atoms we use, the level scheme. We use rubidium. So we just shine lasers over the entire array, so a blue laser and a red laser. And so now we can totally ignore the details of the MO physics structure and just say this is a spin down state coupled to a spin up state. So the two of them are very well defined because you control the polarizations of the lasers, you do optical pumping to start with. And so essentially, it's a spin 1/2 system coupled by a Rabi frequency omega. So just to show you that indeed this is a coherent coupling. I mean, this is just a Rabi oscillation between a ground and Rydberg state that you can see on just one atom. And it's reasonably coherent, maybe not as much as what Ferdi has in his lab, but I mean, still it's now becoming much better than it used to be a few years ago. So now if I write the full Hamiltonian that describes this system, so I have the ensemble of atoms that can interact when they are in Rydberg state and that are driven by the laser. So essentially, I will write an Hamiltonian which has the interaction energy, which is pairwise, so Ni and J with the C6 over R6 coefficient. So this is the equivalent of the spin-spin interaction of the Ising model. I will have the omega term, which looks like this omega sigma x, which is the one that couples the two states. And it turns out that the detuning of the laser with respect to the transition amounts to the equivalent of a longitudinal field, the diagonal term. So if I didn't have this sigma x term, it would be a whole classical Ising model. But the fact that I have this sigma x term, which does not commute with the two other parts, makes it a quantum Ising model. And so experimentally, you can vary the parameters. You can just enlarge the size of the array and you vary the C6 coefficient, vary the power of the lasers, and in this way, explore the transition between fully non-interacting system to overwhelmingly dominated by the interactions. Okay, so this is how we implement on a system where essentially there is no spin involved, it's just a mapping. We can implement this Ising model, and I will just show you what we've done recently in terms of quantum magnetism.
Antoine,
just a quick
question on the previous slide. So
the previous slide, huh? Oops.
So in which range can you vary delta with respect to omega?
Delta, it can be varied at will.
But I guess you don't want to be at resonance, so you don't want delta to be 0.
No, you can actually. And a lot of experiments, we actually set delta on resonance. So in this case, we only have the non-diagonal and these interaction terms.
I see. Okay, fine.
But this is something we can, I mean, when I say you can take delta as large as you want, it's not completely true because there are some rotating wave approximation in the
No, sure. I know the business. Sometimes I was thinking, somehow I was thinking that you didn't want delta to be on resonance But
I will show you. It will. I hope it will become clear when I actually describe the phase diagram in a second. And we're going to see that actually experimentally we vary omega and delta.
Okay, thanks. Thanks.
Okay, so exactly. So let's go and try to implement this Ising model in 2 dimensions. So we're just going to consider, to make things simple, just a square array. I will consider that when there is a gray ball, it's an atom which is in spin down, so the ground state. And we're going to set the parameters in such a way that actually 2 atoms that are sitting next to each other interact strongly, and then there is 0 interaction. So it's really the nearest neighbor interaction, which is a good approximation of a van der Waals interaction. There are details that I will tell you in a minute. So essentially, in the Hamiltonian, we set the parameter in such a way that the omega is on the order of the interaction strength. So now if you ask yourself, so what's the meaning of this? It means that if I have a Rydberg atom here, I cannot have another one within a sphere, which essentially is a radius A. It's called the Rydberg blockade, but it's not essential for what I'm going to discuss. So now if I ask myself, how many of these spheres can I put in the array? I mean, the most tightly packed configuration is this staggered configuration, which you have here. I mean, if I add 1 extra atom, so it's at 0 energy cost. If I add 1 extra atom, then it will cost me an energy, which is A6/A6. Of course, I have 2 configurations that are degenerate, so either this one or the other one. But so those 2 configurations are called the Néel configuration, and it's Néel anti-ferromagnetic configuration. So now, of course, things are more complicated because it is a quantum Ising model driven by 2 parameters, as was just pointed out, delta and omega. And it turns out that people have looked at this phase diagram since the early 70s, and they found out that for the square, you essentially have a paramagnetic phase separated by a quantum phase transition separated to an anti-ferromagnetic phase, which is exactly this Néel order when you have 0 coupling strength. Okay, so this is the phase diagram. The thing I would like you to realize, because for me it was kind of a shock, is that this phase diagram in 2D is only known by quantum Monte Carlo. There is no analytical solution to the problem. And the second is that it has never been implemented in 2D. So which is kind of shocking, because in 2021, 2020, that was the first experiment where we could implement this in 2 dimensions in a fully quantum instance. And despite the fact it has been explored as early as 1970, people are still discovering new phases. So for example, if you remove the nearest neighbor configuration, you will find out that close to this quantum phase transition line, there are some extra phases that appear coming from the tail, the long range tail of the interaction. So I'm not going to make a big fuss of that. I mean, the group of Misha Lukin has looked at that experimentally very recently, as I will mention. Okay, so now what we're going to do, we're going to explore this phase diagram. So we're going to vary the parameters omega delta as a function of time, and we're going to drive the system from the ground state where all the atoms are pointing down. So essentially it's the paramagnetic phase, if you wish. And we're going to try to drive that through the quantum phase transition into the anti-ferromagnetic region. So let's try to do this. So we start with the atoms all down. We sweep the lasers, detuning and frequency, and we take a final image of what is going on. So this is the initial array that we have. So each of the bright dot is 1 atom, so 10 by 10 array, defect free, so 0 defect in the structure. We take a final image, and what we observe is that every other atom is missing. And it turns out that for us, a missing atom means an atom that has been placed in the Rydberg state, because the way we do the detection, it's not too important. So what you've got here is just a perfect realization of the anti-ferromagnetic order following an adiabatic, quasi-adiabatic preparation. Of course, the problem is that it doesn't work all the time, and it should not, because essentially when the size of the system becomes larger, it's harder and harder to be adiabatic. But still, if you just try to do the statistics of the state that you have prepared at the end of repeating this experiment many, many times, you will find that a few % of the time of the realization, out of the 2 to the, in this case, 64, because it was an 8 by 8 array, you will have dominant states that are the 2 degenerate Néel states with almost equal probability. So this machine is able to prepare with a high probability, so to speak, the Néel states. What you can
excuse me.
Sure.
What do you sweep? here you sweep delta or a combination of delta?
I will show you exactly the ramp later on. For the moment, I just sweep omega and delta to actually follow exactly the path I mentioned here. So we first increase omega, then keep omega constant, sweep delta, and then sweep down omega.
Okay, thank
you. So we really go through this phase diagram almost the way it's represented here. So the second quantity we can measure, it's not only just the snapshots where we look at where the atoms are excited, but we can also measure the correlation function. So essentially, we can ask ourselves, when we repeat many realization of the experiment, including imperfect realization of the anti-ferromagnetic state, we can ask what is the probability that if you have one atom up here, you got another one up at a distant k sites away. So it's a 2D map in this case, and what is represented here is positive and negative correlation. So red appears as positive correlation, blue as a negative correlation, and you do see this kind of checkerboard pattern that signs the fact that this is an anti-ferromagnet, and an anti-ferromagnet with a very long coherent length. So you can extract from an exponential fit the correlation length, which is on the order of the size of the array. So typically this is about 9 sites, while the array was 10. I mean, I should point out that also the group of Misha Lukin has done this, and there are 2 papers on the archive which appeared at the same time. And also the largest array we've been able to explore, I'm not going to give you too many details, but it's almost 200. So this is the largest system we've been able to prepare in an anti-ferromagnetic configuration.
So these are the adiabatic state preparation that you do. In some sense, you're saying there is no big issues crossing the phase boundary.
No, there is. That's not what I'm saying. I'm saying that if you repeat the experiment many times, you have a lot of
high fidelity of getting the states that you want.
But of course, it's becoming harder and harder when you increase the system size because the gap closes. And this is exactly what I'm heading at now. So let's try to benchmark the dynamics. So in a sense, we try to compare the dynamics of the system, which is driven across the quantum phase transition through the phase diagram. And let's try to see if we can calculate what's going on and in a sense benchmark the machine. So Arne, just for you, so this was the setting that I was mentioning. So first you increase you increase the light, so the Rabi frequency omega, and then you sweep delta, and then you go back down in omega, and you switch at different times. So essentially, what I will show you is one possible observable we've looked at, which turns out to be the magnetization. So essentially, the magnetization counts the number of spin up in one of the 2 bipartite lattice minus the other one. So that's the thing which would be 1 if you had perfect anti-ferromagnet. And we're going to stop at different points across the phase diagram and measure what is the magnetization. So this is the kind of results that we had, like for a 6x6 array, 10x10, and we've done it up to a 14x14. And the thing which I show you here is the benchmark against theory. But the theory is hard. Of course, it's not an ab initio theory. It must include the dynamics. So it's a matrix product state type of calculation that was done by Andreas and his student in Innsbruck. And just to give you an example, this is the largest simulation that they've been able to do. This simulation includes all the imperfections that we have independently calibrated in the experiment. And so essentially the fact that the atoms are slightly at different positions from shot to shot, I mean, the various things that we have, including the detection error. And just to get one of the single curve, which is in gray here, which corresponds to one particular trajectories for one instance of the disorder, on a big cluster, it takes 5 days to get the results. So you see that the machine now does challenge the theory. And the thing which is kind of neat is that the theory agrees reasonably well with the experiment. So it seems that indeed we are now in a regime where the experiment can go well beyond the theory, and we've benchmarked it as much as we could up to about 100 atoms, which is kind of the limit where you can do these dynamic calculations. So just to conclude on this, what I would like to say, so that the other thing that we have explored is the triangle. The triangle is interesting because now you have frustration in the thing. So we still haven't seen frustration. It's very complicated to know what to look at exactly. But we have also explored the phase diagram of the triangle with the hope of trying to infer something about frustration in the system. But once again, the thing I would like to emphasize, and together with the work of Misha Lukin, is that this is the first time that this 2D Ising model has been implemented. I mean, of course, it looks a bit bizarre to say it this way because, I mean, you say, well, I mean, just take a sheet of atoms in a real material. It could implement very well the Ising model, but actually it turns out that it does not because all the planes are coupled. So, I mean, doing it in 2D is actually challenging in real materials. Okay, so this is maybe a natural break before I move to the other topic. So maybe if we want to discuss a bit more about that, would be a good time for me to stop if you have questions, or otherwise I move on. So.
There was Alexei had a question.
I actually had, well, now 2 questions, but fine. So I'll start with this one, the triangle. I actually wanted to ask just that, and you mentioned this. So what do you mean that this frustration cannot be seen? Because I saw immediately when you said, okay, well, you have the perfectly controllable, arrays, then, okay, the first thing is, okay, well, make a triangle and just have a look and see what happens and observe frustrated systems. I mean, why not? So what is the problem there? Like, why okay. Don't you show the results?
So I don't have the slide with me, so I cannot show you. But essentially, okay. The phase diagram for the triangle, it looks like this. So you've got a 1/3 phase and a 2/3 phase. So this is again omega as a function of delta. So if you are in the 2/3 and 1/3, essentially it means that you place one every third atoms in a spin up, the other one down, or vice versa. So the frustration occurs essentially here. Okay, so this is in this very fine parameter range between 1/3 and 2/3. And it turns out that it seems to be a fairly narrow window in the phase diagram, which is a bit difficult to actually control. That's the first thing. And the second thing is that, so we've done that and we've explored this. So we measure the magnetization across this, but we don't see anything particularly special that would be a smoking gun, or very clearly there is frustration, because essentially there is no criteria. Frustration, the first thing you can say is that, well, I mean, you've got a massive degeneracy in the ground state, but how do you measure that? You must measure the entropy, for example, but the quantum entropy, it's an entanglement entropy, for example. It cannot be, or any entropy, it cannot be a thermodynamic entropy, because it's essentially zero temperature physics that we're doing here.
Yes.
So this is, we are lacking a bit the observables to be able to decide. So there is a prediction which says you should be in a region here, which is called the order by disorder. And so in this region, we try to look at this, and there is a prediction that the magnetization plotted in some units in complex plane should look like a ring. And while we haven't seen the ring, we've seen just a field circle, but the ring would be the signature of the order by disorder. I mean, would be, but not, it's not even sure. I mean, the theorists are still doing the calculation to come up with a real criteria, which is rock solid.
Okay. I see. Thanks.
Could you maybe say a few words about the experimental sequence and like how long does an experiment take and how often do you have to prepare the lattice again and so on?
Yes, so it's a very good question. So the cycling time of the experiment is about 250 milliseconds. So essentially the experiment runs at 2, 3, 4 hertz. Okay, so what do? You just load the magneto-optical trap. From this magneto-optical trap, you load the tweezer array. The array, you need to move the atoms within the thing, which is not too essential for what I'm going to discuss. Then you do the Rydberg excitation, which essentially take microseconds. So it's a very tiny amount of the time. Then you take a final image. So at the end of the day, it's very frustrating, but the longest time of the sequence is to take the image and decide where the atoms are. Okay, it takes 100 milliseconds altogether. And then you but when you do a measurement, it's a destructive measurement. We lose the atoms that are in the Rydberg state. So you need to refill the thing. Typically, for all the data points I show you, we repeat about 1,000 times, which corresponds to about 10, 15 minutes for each of the points. And yes, and then you repeat by varying the parameters. So and the thing which is important with those machines is that they operate at a fast cycling time, so that you can accumulate a lot of data. It's absolutely critical if you want to build statistics, obviously. So,
thanks.
Can you comment a little bit again about this interplay of the size of the system and the fidelity at which you generate many-body states? Because after all, what you are saying essentially is that you are creating many-body states of these two-dimensional spin models, but actually how big you can do your system matters. And somehow I understand that you cannot do it so big because otherwise when you prepare your states, you're gonna get troubles with defects produce it in the high energy manifold.
Yes.
So you mentioned this at a certain point, and I'm not sure I found it.
Okay, so at the moment, and it's true both for Misha Lukin and for us, the largest arrays that we can handle is about 200, 250. Okay. At this level, we start to see the influence of the non-adiabaticity. Of course, we've got a finite time to do the experiment, so we start to see that it cannot be a perfect preparation. You can twist it the other way around and say, well, it's an advantage because it allows you to study the dynamic through the quantum phase transition. You can look at the Kibble-Zurek type of mechanism, which is exactly what Misha did. We also have data on this, and extract the critical exponent. But of course, when it comes to preparing the many-body ground state, you're doomed.
Right, but that's exactly the point, that in order to start any non-equilibrium dynamics, you need a faithful state preparation. So it's true that you can see it as an advantage, but you also need, let's say, control to prepare your initial state. Anyhow, maybe more as a theoretician, my simple question was, how does the fidelity scales with the size? So do you get an algebraic suppression, an exponential suppression? Because this is what you want to know, right? How many repetitions you need to do for a given size, for a given target size is what will limit your many-body theory, in a sense. Am I clear? I can be more precise if you want.
No, but I understand the question. Unfortunately, I cannot give you a real answer to that because, I mean, the theories cannot do the finite size scaling. It's too hard. Beyond 100, we don't know. Because doing the...
Not even an estimate paper. So I'm sure somebody calculated it. I know that 2D quantum.
Yes, so in the paper of Misha Lukin, they were saying that they've got some kind of scaling that they extrapolate, that they have something which scales exponentially. So essentially the fidelity or the probability to get...
That's what I feared.
0.97 to the power n. We could also extract that from our data. It's about the same, maybe a bit smaller, I don't know. The point is that, you know, for both experiments, we are not only plagued by the finite gap, we're also plagued by other imperfections. So this 0.97 can be a mixture of non-adiabaticity and all the other imperfections that also scale with the number of atoms.
I see.
If now coming to the idea of can you generate the given initial pattern, it depends what you're looking at. If you are interested in generating the anti-ferromagnetic order, at the end of the day, I do not need to do everything I'm doing here with the sweep and the thing. If it's just an AL order that I want, it's very easy. I just excite every other atom, and that's it. Okay.
I agree.
Of course, now it's more a problem if you want to find the ground state of the XY model, because the XY model, there is no classical configuration. So you need to do the sweep. And there I have no answer to give you because, I mean, if we have an infinite amount of time, of course, it's going to
sure.
fidelity, but we don't. So that's clear that there is a limitation in how what's the
but clearly you have been very good / I don't know if it was also a little bit of luck, because 250 you said is a huge number. There will be no simulation, I mean, capable to do much better than that. I don't know what Andreas is.
Andreas, this is, I mean, he was saying that for the 14 by 14, it's out of question. I mean, they
exactly.
Can yes.
Exactly. So your experimental size is already, despite all these complicancies, way better than any theoretician could.
No, you're right. But, you know, for example, when it comes to studying triangular arrays turns out to be much more sensitive to boundary effects. And so this is an issue because it means that, you know, the kind of triangular cluster that you have here, that you can see on this picture, the bulk is not so large. And so trying to say that you are looking at bulk physics with finite size system, it turns out that for the square, it's pretty good because the bulk is reasonably robust. For the triangle, it's already an issue for the 2/3 phase, for example. So we would definitely like to go to larger number of particles. And I think that we should be able to go to 1,000.
But it's already great. I mean, this was my implicit comment. I mean, I needed to understand because it's already, I mean, anyway, super competitive. So thank you.
No. Are there other questions?
And what if you were to do this in 3D? So I mean the normal, the square one, like the, you know, not the triangle but the squares, but in 3D. I mean, because that would be even the easy model in 3D.
Well, I mean, that would be first cool, and second, it would allow you, for example, if you have kind of a cube, if you wish, but which is empty, you would implement the 2D model, Ising model, with periodic boundary condition even. So we have not done it for very mundane reasons, which is that if you want to have the beam, I mean, when you do 3D stuff, I mean, of course, you've got arrays of planes, and you need to cover with your excitation laser all the arrays, and they are reasonably separated, and it makes it very challenging experimentally to do that. It's not impossible, and this is something we're thinking of doing. What we can easily do are 2D, two bilayers type of physics. That is the thing which we will try to do reasonably soon. Really doing the full cubic stuff at the moment is challenging for laser power resources, essentially. So.
Okay, thanks.
Yeah. Other questions? So if you wish, I can move on to the second part of the talk. So I will skip some of the thing in the second part because otherwise we're going to be a bit too long. But essentially, I would like to introduce you to this idea. I mean, this is something which is a bit less known, I find, and which I find kind of interesting, and which is also doing many-body physics, but looking at it from a quite different context. So the idea now is to look at light scattering in dense atomic ensemble. And I will try to show you that actually this also implements Ising, often not Ising model, but the spin models like the XY model. So I will probably skip the scattering in a chain and try to look for subradiance. So what is the point? The point is actually much easier the question is much easier to ask than everything we've discussed so far, because this is kind of daily life experience. You just have a cloud of atoms, so it can be the atmosphere or whatever. You just have light, which goes onto this, and you ask the question, okay, how is the ensemble of scatterers scatters light? I mean, of course, we kind of have the feeling that we all know that very well. Essentially, the light drives the dipole radiates, and you've got the interference of all these things. But the problem is that now, if you have the laser light or the light which is close to an atomic resonance, and on top of that, the atomic sample is dense, you may have very strong interactions between the dipoles. And therefore, you cannot any longer take your textbook that Jackson or whatever and assume that it's just the interference between the field, because you do have to take into account the interactions between the light-induced dipoles. And in this case, the interactions becomes completely collective. But now if I look at the quantum part of description, I mean, what is these interactions between two dipoles? It's actually an exchange interaction. It amounts to taking each of the two dipoles as two-level systems. I have one atom in the excited state, the other one in the ground state, and this light-induced interaction is nothing but the exchange of state by these atoms going down while the other goes up by exchanging a photon. It's a virtual exchange, and so at the end of the day, what you implement really is an exchange Hamiltonian. This is the sigma plus sigma minus types of Hamiltonian times a VDD, which is the coupling strength. And the VDD, I mean, it's reasonably complicated to calculate from fully quantum perspective, but I mean, you can do an intuitive derivation of VDD by just saying, well, this is the interaction between two classical dipoles. And that you can open Jackson again. You have the field generated by a dipole, which interacts with a nearby dipole. And what you find out is that you have many of these terms. The radiation term, 1 over r at long distance, with the e to the ikr for the propagation. You've got the dipole part, 1 over r cube at short distance. And you have this induction part in intermediate regime. Okay, so now what you have is an Hamiltonian which is no longer a coherent Hamiltonian in the sense that it's non-Hermitian. Okay, so what you are really simulating is a dissipative spin model. But the thing which is interesting is that it's dissipative, but with the imaginary part and the real part. So the imaginary part is the dissipative part, and the real part is the coherent part, and they are related because they are the real and imaginary part of the same quantity. So it's a collective scattering that you're describing here. And so what you mean by dense is the fact that the atoms are smaller than the wavelength of the light. In this case, it turns out that if you do the math, the dipole-dipole interaction becomes larger than the line width of the transition. So the consequence of that is what? Is that now if you look at the scattering from a quantum mechanical picture, one atom is excited and it can either decay by emitting spontaneously photons, or it can exchange its state via this quantum mechanical process with a nearby atom. So this is the quantum mechanical version of this light-induced interaction, if you wish. Okay, so it's even more complicated, to tell you the truth, than actually the Ising model that I was showing to you before, because it's a completely driven, many-body, open quantum system. So you've got every buzzword in the same thing to tell you how complicated the thing is. People have started to look at this. So usually looking at random ensembles. So the random ensembles is the easiest to prepare. So you just either look to hot vapors. Hot meaning that it's room temperature or hotter. You just shine a laser on that and look how it scatters light. We've done that in dense cold atomic cloud, and people have also looked at that in very large dilute atomic cloud. Okay, there is a whole set of experiments. Those experiments are reasonably recent, and all of them are less than 5 years. And so just to, once again, it's not like physics known since the beginning of the 20th century. All these actually were operating in a regime where Jackson physics just fails. Okay, because we are close to resonance and the interactions between the dipoles is very strong. So now, one thing we would like to do experimentally is, instead of relying on a random ensemble, you would like to structure the array. And the reason why you want to structure the array is that now, instead of having, for example, this interaction in energy with scales like e to the r kr, the propagation phase of a kr, if now you've got a random ensemble at a given location in the cloud on one atom, you've got the interference of all the fields, but because of the random phases, this interference is reasonably weak, and therefore the effect of the interaction is pretty small. If instead you structure the array, then you're going to recover a large influence of the dipole-dipole interaction, which is to say the field scattered by all the other atoms at a given place. And people have looked at that. I mean, theoretically, I mean, you just take a chain of dipoles, and if you have a way to structure that, you can induce interaction between the dipole, which leads to strong collective effect. So for example, you can have a configuration where all the dipoles are actually in phase, in which case all the dipoles oscillate, and you will have a subradiance effect in the sense that all the field will interfere constructively, and the ensemble is going to release energy at a faster rate than any individual atoms. On the opposite, you can have what is called subradiance. So subradiance corresponds to states that have, with the dipoles that have phase, that are in phase opposition, and therefore all the field scatters will interfere destructively, and essentially it acts as like a memory. The thing keeps the excitation in the ensemble. And so people have said that essentially, if now you manage to structure your chain in such a way that the interparticle distance is smaller than lambda/2, then in a chain you should have many of these subradiant states, and so essentially those are like guided mode through the chain. So the excitation, the up excitation, if you wish, stays along the chain and does not decay unless you look at the edges. So that's only why it can decay. And so people have proposed to use that in order to build new atom-light interfaces, to optimize clocks, because you do not want to have the shift induced by the interactions, and even to investigate topology on nonlinear optics. And there was an important experiment last year from the group of Emmanuel Bloch, where they showed that if you have a 2D plane of atom, it can act at an almost perfect mirror if you take into account the fact that those dipoles interact. Okay, so we looked at that in our case, and we've been able to look at the scattering in small atomic chain. So I'm not going to discuss that because it will take an extra 10 minutes. I will just switch to the second thing I wanted to discuss, which is subradiance. So as I mentioned, there are two ingredients that we would like to have: the chain, which is structure, but also subradiance, which is the fact that you can have an orientation, relative orientation of the dipole, which leads to a very slow release of the energy from the ensemble. So this is something which is much less known than subradiance, and that we have observed in our cloud, and I would like to show you that. So people want to use subradiance as a mean to store photons in the media, because if you got very long-lived state, if you can store a light excitation in this long-lived state, it's going to take forever to decay, and therefore you can store the light in. So there were lots of proposals in the recent years from prominent groups trying to explore this, but essentially what you need is a medium which is able to sustain subradiance, a way to store the light, and a way to release the light. And what I will try to show you is the point 1 and 2. So essentially that we can have a medium where we can see subradiance, We are not going to store it in a controlled way. We'll show you how we prepare subradiant excitation. And then we want to release on demand the excitation. So let me just...
Sorry, very
sure.
quickly.
Yes.
One clarification. You mentioned non-Hermitian Hamiltonians at the beginning.
Yes.
But I guess that there will be some jump terms too, right?
Yeah.
So,
no, you're completely right. This non-Hermitian Hamiltonian, this is in one particular approximation, which is the weakly driven approach. Otherwise, you are completely true. You need to write the full master equation with a Lie-Flat, which is collective.
This is what kept me thinking. So when you made all these comments are for non-Hermitian plus jumps, right?
Yes.
Okay.
Yes. Yes, here, just because otherwise it's just too complicated to understand, I find I kind of jump from, these kind of classical pictures of dipole, because this is the underlying picture, but it's only valid, strictly speaking, in the weak excitation regime where you do not have many excitations in the system. Otherwise, it's not possible to interpret that in a classical way.
I only needed to be put back on track. Thanks.
No, but you're completely right. Yes.
It was only clarification.
So for those of you who have never seen subradiance, so let's try to come back to these exchange mechanisms. You've got the sigma plus sigma minus Hamiltonian. At the end of the day, you can diagonalize this and you've got a symmetric and antisymmetric combination. It turns out that the antisymmetric combination, which correspond to, again, those two dipoles in phase opposition, can have a lifetime which is extremely long. So this is the thickness of the line. It goes to 0 when the atoms are close to each other. So essentially, the atoms are so close that they have 0 dipole in as the sum of those two. This argument, of course, it can be generalized to an array of many atoms. If I just take many atoms, one is driven by the field scattered by all the other one. So it means that I have a linearly coupled dipole system. I can diagonalize this system in the very same way I've done here. And I define a mode which corresponds to a particular configuration of the dipoles across the cloud. And some of these modes have a lifetime which is larger. It's a collective lifetime, decay rate, which is larger than the single atom decay rate. Those are the subradiant state. Others have a decay rate which is much smaller. So I mean, you can, for a particular configuration of the atoms, let's say 300 randomly distributed in this box, I can diagonalize this and I find that I have some states that are subradiant in the sense that they have a gamma, the line width of their state, which is much smaller than the gamma of a single atom. Okay, so it's just a generalization of this. And once again, the classical pictures is just dipole that are in phase opposition somehow. Subradiance has already been measured. It was observed for the first time, not that long ago, actually, in 2016, as a non-exponential decay of light following, so it was in the magneto-optical trap, so large cloud of atoms. You drive with the laser, you switch off the laser, and you look at how the fluorescence is released. So it was done in the group of Roman Kaiser in Nice, and this is a very nice experiment. So what we're going to do is to operate in a different regime. We're going to operate in a regime which is much closer to the regime of decay, where you have a decay, the Rydberg decay, where you have many atoms within lambda cube. Because then what is different with respect to their large ensemble, which is quite dilute, is the fact that now in our case, we will have to take into account all the interaction terms, 1 over r cube, 1 over r square, 1 over r, in order to understand the system, because the atoms are really sub-lambda, closer than lambda. And so what the people had found for the subradiant decay in a cloud of cold atoms is the fact that the longest lifetime was proportional to the optical depth of the cloud. And it turns out that in our case now, if the cloud is much smaller than the wavelength of the light, it can only depend not on the optical thickness, which is a meaningless concept in this case, but only on the number of atoms that we have in the cloud. So the regime is reasonably different. So that's what I'm going to show you. So how do we do that? We again start from a dipole trap. So it's again a tweezer, but instead of placing one and only one atom in this tweezer, we are able to place many atoms in this tweezer. So typically up to 5,000 atoms. They are extremely hot by laser cooling standards, but the density is extremely large. And that's what matters for us, because it means that the atoms are at a distance which is smaller than 1 over k, which is lambda over 2 pi. And so what we do now, we're going to excite this system. So we have this elongated cloud, and we send pulses of light, reasonably short, 419 nanoseconds. The system reaches equilibrium, and we measure how the light decays after we switch off the excitation. So the light emitted by the cloud. So essentially we measure along two different axes. It's not too important, but we excite and we measure the light emitted by the ensemble. And so if we have a small number of atoms in the trap, so typically about 300, we've got the exponential decay. This is in log scale. What is this dotted line is just the solution of the Bloch equation for a single atom driven by the laser pulse that we can measure. And you see that it fits the data very well. So it's linear, it's the exponential decay that we know very well. Light is emitted exponentially. Now you increase the number of atoms in the very same sample. And you do see now that first you observe subradiance at the beginning, and you've got a much longer tail, which is the signature of subradiance. And so what we have measured, but once again, it's much denser than the case I showed you from the Kaiser experiment. And indeed, we try to make sure that the scaling parameters for the decay rate or the lifetime, instead of being the optical thickness, was not the number of particles, because we operate reasonably close to the decay regime. So we measure the decay rate as a function of the optical density for various conditions. So it's the same number of atoms, but at twice the density, or the density over 2, or we just keep the number of atoms constant and just vary the density by squeezing more or less the trap. Essentially, it seems that there is no universal law, but as soon as you plot all the data only as a function of the number of atoms instead of the optical thickness, for example, they kind of collapse on the same universal curve, which indicates that indeed in our regime, close to decay subradiance, the only relevant parameter that governs the lifetime is the number of atoms. We have also studied that as a function of the intensity, the detuning. Okay, it's not too important. All right, so this is the signature of subradiance in the cloud. So now let's try to look maybe to future possible application, which is you would like to have a medium which exhibits subradiance. You would like to store the light in the subradiant excitation and on demand release it. The storage part we have not done. Essentially, the way we store, so to speak, in the stupidest possible way, we just wait. When you have excited the atoms, the cloud, essentially you excited the superradiant, the subradiant mode, so long-lived, short-lived type of states. Then you let the system decay. It decays non-exponentially, but if you wait long enough, you will only have left the longest lived state, which are the subradiant state. Okay, so if you are in the tail now here, essentially you are left with the longest lived subradiant state. So this is in a sense storing the excitation by just waiting until all the other excitations comes out. Okay, and so now what we want to do is to release this subradiant excitation on demand. So how do you do that? I mean, I just remind you that subradiance corresponds to the coherent coupling coming from the resonant dipole-dipole interactions between all these emitters. So now, if you have a way to break the coupling between the emitters, it means that they will become independent again. They are no longer coupled with each other because the interaction is no longer a resonant dipole interaction. So the idea now is exactly to do that, is to make all the atoms at a different detuning in such a way, the different resonant frequency, in such a way that they are no longer coupled. And how can you do that? Just by switching back the trapping laser. The trapping laser creates a light shift on each of the atoms, but this light shift depends on where the atoms are in the trap. Okay, so if you apply a strong enough light shift, each of them will see their transition frequency shifted. And indeed, if you do the calculation for the kind of light shift that we can do, initially, the decay time or the states would be spread over a large transition, which is a large range, just because you have a lot of coupling between these tweezers. And now when you apply the dipole trap, you are essentially back to one single lifetime, which is the independent atom lifetime. And what you expect when you release the trap is that as soon as you switch on the trap, you expect to have a burst of intensity coming out from the trap. This is essentially the signature of the fact that you are releasing the subradiant excitation. So let's do that in the experiment, and this is indeed what we see. So you just wait until you are reasonably close to only having subradiant excitation. You apply the dipole trap, and what you see is this extra amount of light which corresponds to the release of the subradiant excitation from the system. And you can do that at different time. and you will always, and you will always see this release of the excitation. Okay, and back to essentially the single atom lifetime. So this is a way of showing that by, in a sense, tailoring the collective state that you have created by changing the relative phase between all the atoms, you can break the collective coupling and make the atom release their energy in free space. Okay, so that's all I wanted to tell you. So just as an outlook on this last part, we are also looking at subradiance in this system, so the early stages, so that's what we're looking at. And ultimately, what would be really interesting to look at, because it has never been looked at experimentally, is what is the statistics of the light which is emitted during, in the sense the G2 function, during the subradiant or superradiant excitation. So, and the reason why it's interesting is because in a way you are using the light in order to probe the non-classical statistic of the light that we hope we will find, in order to probe the interactions inside the system. So you've got some kind of probe of the many-body character of the interactions between the atoms by looking at the collectively emitted light. So this is something we're trying to do, but there are challenges ahead that we're trying to solve. Okay, so this is the end of what I wanted to show you. So just, I have not gone too much into the details of what we do, just going to flash a few ideas of experiment, but hopefully I convince you that those platforms are kind of interesting to look at quantum optics, many-body physics, either in a coherent or in a dissipative regime. And it can be used for either quantum simulations or new type of atom-like interface and so on. And with that, I would like to thank you for your attention.
Yeah, thank you very much. Very nice talk.
Very nice talk. The floor is open for question, and we have already Dima raising his hand. So well, you can raise your hand, you can ask questions in the chat, we translate them then, and we can. Well, that's very disciplined. So everybody's raising their heads now. So Dima Budka, please go ahead with your question.
Thank you so much. That's very, very interesting talk. I have a couple of questions about this collective scattering.
Yep.
So one question I have is that there is this very, very old phenomenon of radiation trapping, and I'm curious, where does radiation trapping come in here, and how does it relate to this regime that you described? That's number one, and maybe somewhat related. I don't have a good feeling currently for the numbers, but let's say I have a vapor cell of rubidium atoms, sort of an object like we use every day. Mm-hmm. Can you get to the collective regime with that?
Okay, so two excellent questions, thanks. So the first one about radiation trapping. So that's true that for the first experiment of Robin Kaiser. So what is radiation trapping? First, the way people understand that is essentially you've got a photon which is spontaneously emitted by an atom and which is recaptured by a nearby atom. And you can write some kind of model where essentially this radiation trapping looks like a Coulomb force between the two atoms because, you've got the scattering cross-section. The photon scattered by one atom is recaptured by the second one. And so that was something that, for example, limits the density of magneto-optical trap. So then people, as you said, have looked at that a lot in the 90s and so on. And so, but that's usually a problem when you've got an optically thick medium. And so that's the reason why in the case of Roman Kaiser, they spent a lot of time to identify the regime where they were sure that it was not radiation trapping. How do you do that? You go very far from the resonance instead to make sure that the medium is reasonably transparent. So it has a drawback, which is then you've got much less signal and blah, blah, blah. Okay. In our case, we've also explored that. We tried to go away from the resonance and we saw no deviation whatsoever in the time that we measured at long time. And on top of that, in our case, as I try to convince you, we do not have an optically thick medium. The medium is sub-lambda in a sense. So the concept of radiation trapping in our sub-lambda system is in a sense meaningless. So that's the reason why you do not have to care too much about that. So now just to finish off on this, because I think it's an interesting question, I discussed that a lot with Robin Kaiser. For the moment, no one has any theory that is able to bridge the gap between the two regimes. it seems that it should be a crossover going from the radiation trapping, which is kind of a real exchange of photons in a way, to this virtual exchange of photons. But bizarrely enough, we do not have a unifying theory bridging the two regimes. But in our case, in a sense, it's not the right way to look at this because the sample is too small. So I've told you as much as I can about this, but it's enough for Dima, or you want to discuss more about this?
Yeah, super. This is great. But the second part is if I take a vapor cell.
Yes.
You had one of these nano cells probably made in Armenia.
Yes.
Shown on your
because
slide,
we've
but
done it. Yes.
A normal vapor cell.
No, so you can see collective effect. The problem is that the main issue is that if you want to have at the same time the strong density, it's at the cost of a high temperature, usually a lot of absorption, which is the reason why you go to thin cell, and a lot of Doppler broadening. And the Doppler broadening makes the interactions non-resonant. So you can have traces of them, and actually we'll measure that together with Charles Adams. We have a paper where we look at the Lamb shift, the collective Lamb shift in this system. But it's only a weak effect because of the fact that the dipoles have different frequencies due to the Doppler shift. So sure, you can see collective effect, but they are much more difficult to actually, for example, it's an open question whether subradiance could be seen in such media. Yeah.
Thank you so much. Really fascinating. Really fascinating.
Great. There's another question by Jamia.
Hi, Antoine. Just a simple one. Maybe I missed the motivation at the beginning, but somehow realizing subradiance and superradiance in cavity QED with cold atoms was done in a lot of groups before, right? Esslinger, Hemmerich, a lot in the US. So, which is, I'm sure there is a difference here. I'm sure you have a comparative advantage. What is that?
Okay, I wouldn't claim it this way, that there's a comparative advantage. So first, we have to be very careful about what we're discussing. So superradiance, for sure, it has been seen by Tilmas and Esslinger in a different context. So for example, this cavity QED, where you got this Dicke model, which self-structure. So very clearly, this is a superradiance. Superradiance have also been seen in the old days, you know, in beams, subradiance, much less. Subradiance, it has been seen with two ions placed at a distance of a few lambda, and where they show that indeed the decay was modified. People had seen that in a Rydberg state, but it was Pierre Pillet who did it in the late 70s, but it was a bit unclear exactly how they measure that. So subradiance is not so well known, and has not been studied as much as superradiance, which is much easier to see in a sense.
At the risk of making prominent my ignorance
Sure.
in a topic in which I should be instead knowledgeable, that's somehow surprising, right? Because as an innocent theoretician, I think, well, it really depends just changing the wavelength of the photon in the cavity with respect to interatomic distance. I can go from subradiance to superradiance, but apparently experimentally, no.
No, but it is challenging to do. I mean, for example, indeed, and those experiments are reasonably recent. They are probably 3 years old. Gerhard Tremp, but also Dieter Mesche, they have some experiment where you put two atoms in cavity, and indeed they can vary by placing the atoms with optical lattices at different positions in the thing. They can see the subradiant and superradiant mode, but just for two atoms.
Interesting.
So no, the subradiance is hard to control. Experimentally, it was very hard to see on bulk medium, essentially because you see it's something you have to look at the very long tail. So for a long time, you have to realize that actually people didn't know how to prepare such dense cold atomic ensemble. So I'm not making too much of a fuss about that, but I mean, at the end of the day, we've got laser cooled atoms at a density which is 10 to the 15 atom per cubic centimeter. This is a lot. And if you take a usual laser cooling experiment, including BECs and quantum degenerate gases, usually the densities are 2 or 3 orders of magnitude smaller. But 2 or 3 orders of magnitude smaller means that the interparticle distance is larger than lambda. And therefore, it's much harder to see the effect. So having at the same time, so how do you do so you have two ways to do that. Either you've got an extremely optically thick medium, which is the approach of Kaiser. So there the photons, in a sense, they bounce a long time, or they interact with a lot of atoms many times, and that enhances, in a sense, the interaction between the atoms. Or you do what we've done, which is you take a much smaller number of atoms, you try to make the sample as small as possible, and then the density is very large, and you can see the effect. But mind you, if you look at the effect, you see that subradiance occurs when you've already lost almost 9/10 of the light. It occurs in the tail, and in the tail it's a nightmare for the experimentalists because you've got the noise. And for example, in the case of Kaiser, they showed that not at 10⁻⁻⁴ as we do, but 10⁻³ to 10⁻⁴. So you are really in the noise level of the detector. It makes the detection much more difficult. So you have to work very hard to make sure that what you are seeing is indeed the subradiance and not the slightly weakly driven.
So a weak subradiance, of course,
yeah.
Very close to the decay transition. Very interesting. Thanks. Very nice. I learned a lot.
Cool. Are there more questions? Maybe since you mentioned it, how do you get the density in your trap?
Yeah, so we play a lot of tricks. So essentially, we start from a dipole trap, which is quite large. So quite large, not so large. It's about 3 micrometers in waist. There we can place 5,000 atoms. And then we have an experimental system where we use what are called opto-tunes. So those are lenses that you can tune electronically, so the focal length. And we use that placed in a telescope configuration in order to squeeze the waist of the tweezer. So you just take your cloud and you squeeze it a lot. So you increase the density by a lot. Of course, you hit the cloud by a lot. So that's the reason why the temperature is so high, despite the fact we start from clouds that are about 100 microK. At the end of this compression stage, it's very dense, but we have lost in terms of temperature. But itself, but as what matters for us is the density. In this case, it's all right.
More questions? So while you are thinking of questions, I'm going to advertise next week's seminar. It's going to be given by Tanya Rousey from GILA in the group of Eric Cornell, and she is going to talk about the experiments that they do there and how they use, I believe, their EDM searches to search for new physics and dark matter particles. So maybe one last question. Does not seem to be the case. So Antoine, thanks a lot for this very interesting talk.
Thanks a lot for the discussion. It's always very nice.
It was great. And then as Ferdinand pointed out, I don't know, maybe it was just an idea by him, but at least it's a nice idea to invite everybody from the Quantum Seminar to actually appear in person, and maybe Paris is not even that far away.
I'm for it. Thank you very much.
Thanks. So Dima, I interrupted you.
No, I just wanted to once again thank Antoine for the really great talk. I really enjoyed it.
Thank you.
All right. So we close the seminar. Thanks a lot, everybody.
Thank
Goodbye.
you.
Bye-bye.
Thank you. Bye.
Thank you. Bye.